Hello everyone. Today we will start in a new topic in our electromechanical energy conversion course. So the new topic is synchronous machines. So in our new material, these are the learning objectives. So first objective is to know the different types of synchronous machines. What are the different types of synchronous machines? We have what's called cylindrical type, we have salient pool type, we have other permanent magnet synchronous machines, so we will know the different types. Also, the other objectives, so to know the construction, like any other machine, guys, we have stationary part and rotating part or moving part, so we will learn the construction of this machine. Also, the objective to recognize the synchronization condition. So what is the meaning of synchronization condition and how can we make synchronizing between synchronous machines and electrical grids? Another objective is to know how to determine the synchronous reactance of a synchronous machine, which is the parameters identification of the machine, like any other machine we discussed. Also, to drive the phasor diagram for synchronous machines at different power factor conditions. So, we discussed before the meaning of phasor diagram, and now we need to drive the phasor diagram for our machine and different power factor conditions. So we know that motor is load, how a load can have different power factor, how a motor can have different power factors. So we will see that in a specific synchronous motor case, because regularly, motor is inductive load, but here the synchronous machine can be controlled to have different power factors. So we'll drive the different phasor diagram for the synchronous machine at different power factor conditions, and we will see how to control the power factor. Also, to recognize the power and power angles in the different cases of synchronous machines. To understand the constant power operation of a synchronous machine. So this is an operating condition of a synchronous machine, and we regularly use this type of control in power plants. So we need to know what is the constant power operation. Also, to analyze the synchronous machine power and torque and investigate the V curve. So what is the V curve of the synchronous machine? And investigate the power factor control using synchronous machines. So these are the objectives for the new material. This can be covered maybe in 3 weeks classes. So let's start today with the introduction to our machine. So like any rotating machine, guys, we will discuss the rotating machine's construction. We have linear machine, we have rotating machine. So we will discuss in our class the rotating machine only. Linear machine is something very specific, and it's used in high-speed trains. So it's related to another topic called translational motion machines, but we are not covering this topic in our classes, so we are focusing only on the most important types of machine that you will see in industry. So the construction of a rotating synchronous machine, like any rotating machine, guys, it has two mechanical structure bodies. The first body is the stator body, or the stator object. On the stator object, we have three-phase windings are wound on the stator slots, keeping 120 phase shift between every winding. So we have three phases, 120 electrical degree phase shift between every phase in order to generate a rotating magnetic field. So what's the meaning of rotating magnetic field? And if the angle is not 120 degrees, will we have a rotating magnetic field or not? So we will discuss this as well in the three-phase magnetic field model and the derivation of the magnetomotive force of the synchronous machine. So we will see what the meaning of rotating magnetic field. Then the other part, the other mechanical part is the rotor. And on the rotor, the magnetic field is generated either by permanent magnets or by applying DC current to rotor windings. So we have two shapes for the rotor circuit. So rotor structure is going to be also ferromagnetic material, and it has different shapes. We will see the different shapes in a few slides. So these shapes, or this mechanical rotor magnetic core, will carry either a permanent magnet or field winding. So permanent magnet, we will have a certain number of magnets to generate or to construct a DC magnetic field in order to allow generating the AC or use the magnetic flux for the energy conversion. Or we can have one winding connected to a DC supply. So in this case, this will need slip rings and brushes in order to connect DC source to a rotating coil, a coil mounted on a rotor structure. So we cannot have physical connection, or let's say not physical, let's say soldered wire, okay, or solid wires. We have to have like what we discussed in the DC motor. So we have commutator and the brushes. So here, instead of commutator, so we don't need to have commutator here because the configuration of the winding and the function is different to the DC motor. So here we will have, instead of commutator, we will have two rings, and these two rings, one ring is going to be positive and the other is going to be negative, and these rings will be connected to brushes. So the winding will have a single polarity all of the time. So it's different to the DC motor structure or DC motor winding configuration. So by the end, we will have just one winding connected to a DC supply through slip rings and the brushes. So this is the based circuit rotor. And the permanent magnet one, the permanent magnets will be installed in different ways. We can install the permanent magnets on the surface of the rotor. So this is one way. So this is called surface mounted permanent magnet machine. Or we can have the permanent magnets inside the rotor core, not on the surface of the rotor core. So in this case, we call it interior permanent magnet machine. And permanent magnet machine, by the way, is used a lot in high-speed motors nowadays, in electric vehicles as well. However, in our class, we are discussing mainly the based field winding, the field winding based synchronous machine. So no permanent magnet machines will be discussed in our class due to the time limitation in our course. And due to the complexity of the permanent magnet synchronous machine model compared to the electromagnet one. So we can consider the permanent magnet machine as graduate topic instead of undergrad topic. So we will focus our discussion, guys, on the field winding based machine. So since now we have two circuits on the stator and rotor, so let's see what are the different rotor shapes we have in synchronous machines. We have actually two shapes of synchronous machine rotors. What are these two shapes? The first shape, guys, is called the cylindrical type. So the first shape is called cylindrical type. So this cylindrical type is used for high-speed machines. Let me show you that in this slide. So this one on the left-hand side is called cylindrical. Cylindrical because the surface of rotor represents a cylinder. So this is why we call it cylindrical type. The other type, guys, is called salient pool. So salient pool because we have saliency in the rotor structure. As you can see, the air gap is not uniform like in the cylindrical type. So the salient pool is non-uniform air gap, and the cylindrical is uniform air gap. And due to this saliency, guys, we have different equivalent circuits for the salient pool one, and this gives more features compared to the cylindrical type. So this is a shape of a salient pool here, okay, and this is the shape of the cylindrical type. In terms of dimensions and applications, the cylindrical type rotor has long length and short diameter. So the diameter of this rotor in high power synchronous generator can reach to like 3 meters. But here in the salient pool type, the diameter of the rotor can reach to 15 meters. So diameter of salient pool is much larger than the diameter of the cylindrical type. And since if we compare the same rating of the machine, so both of the rotors have to have the same moment of inertia, or let's say core volume. So in this case, since the cylindrical type is a small diameter, the shaft length is going to be large compared to the shaft length of the salient pool one. So we do prefer to have the cylindrical type to be the rotor to be horizontal like that. So it's mounted horizontal. However, the salient pool, it's preferred to mount it vertical, which means this X here in the middle is going to be vertical like that. So the rotation of this machine is going to be horizontal rotation, okay, or rotate on the horizontal plane, but this is rotate in the vertical plane. So this is the difference between the two shapes. So we have, in summary, we have salient pool and cylindrical type. Cylindrical type has uniform air gap. Salient pool machines have salient or non-uniform air gap. Due to the big diameter of the salient pool machine, we will have many pools inside this machine. So pool, guys, the pool of winding comes from reversing the current direction inside the winding. So let me draw one more slide here to you. So if we have a winding like that, so here, this is a slot number 1, for instance, slot number 2, and so on, and this is the end of the winding. So if the current is flowing like that, it will return back in the coil like that. And if we return to the winding like that, so still the current is moving in this direction, and so on. So since under the same slot, or if you have many slots having the current moving in the same direction, so between this one and that one, we have one pool. So If the current start changing the direction, so this is gonna make a different pool. This is gonna make a different pool. So since in cylindrical type we have a small diameter, so this is a cylindrical type, D is small. So number of poles here is not gonna be large, it's small number of poles. However, for large diameter salient pool, so this gives us the opportunity to make windings in different pools. So now number of poles here is gonna be large. So for instance, you can find salient cylindrical pools up to 8 pools because we don't have large diameter. However, in salient pool, you can have up to 80 pools. So it's 10 times more. So what is the advantage of having this high number of pools? Actually, this is related to the mechanical source or mechanical energy source selection. So we use the small diameter machines in high speed machines. Why? What is the relation? Actually, the relation is the synchronous speed. So the synchronous speed is 120 times frequency divide number of poles. This is the synchronous speed. So the speed of the magnetic field and the speed of the machine is 120 times supply frequency divide number of poles. If the number of pole is small number of pole, like what we have in cylindrical type, so in this case we expect NS to be high number. But if the number of poles is very high, like 80 poles, so we expect the speed in salient type to be small speed. So mainly we use the cylindrical type and high speed. High speed what? High speed mechanical source, like for instance, the steam turbines, gas turbines. However, we use the salient pool in low speed machines, like in the case of wind turbines, okay, like hydraulic turbines. So in this case, we do prefer to use salient pool machines instead of the cylindrical type. So if we go back to our machines again, you will find that we have high speed machines. So for the high speed machines, we use the cylindrical rotor. Why again? Because number of poles is small. And for this type of machines, guys, you can find it in power plants in several hundreds of megawatts. Several hundreds of megawatts. It can reach to like 300 megawatts or 300 megavolt ampere generators. Okay. And the source or the mechanical source is like in steam and gas turbines. And for the salient pool type, it's used with low speed machines with salient pool rotor, and it has several tens of hundreds of megawatt. So it's not that high rating like what we have in several tens to 100. So it's several tens. So starting, let's say, 10, 20 megavolt ampere, okay, but not like few hundreds megavolt ampere like in large synchronous machine used with steam and gas turbine. And again, guys, you can find this in hydraulic turbines or wind turbines. Okay, so these are the ranges of generators used with hydraulic or wind turbine generators. Okay, so after understanding the construction, we mentioned that we need a DC source for our field winding. So from where we can this we can get this DC source. So this is called excitation. So the expression excitation means establishing the machine flux. So this is the meaning of excitation. So exciting a machine means creating a source of flux for this machine. So what are the excitation methods we have in synchronous machines? We have permanent magnet excitation. Permanent magnet excitation, it doesn't mean that the machine is permanent magnet. However, we can use the permanent magnet to establish the flux of the machine and building up the flux inside the windings. So in this case, guys, the permanent magnet excitation, it uses huge number of poles along with some windings to create this type of excitation. And we don't prefer it in large synchronous machine. We have other types like brush excitation. We use brushes to supply the rotor windings, and you know the problems of brushes. So brushes needs maintenance, and if this is not considered, if the maintenance is not considered, so this may make a lot of problems. This may lead to short circuit or damaging the machine rotor and windings and cause a lot of fires. So this is relatively unused for large synchronous machines. However, we do prefer to use the brushless excitation. So what is the brushless excitation? How can we make or supply the rotor winding, the moving winding, without brushes? So this is called brushless excitation. So let's see the brushless excitation. And again, this is the most preferred one we use in industry, especially for power generation in power plants. So let's see, guys, an example for excitation or brushless excitation for our synchronous machines. So as you can see here, if you can imagine with me, guys, the top part here represent the rotor. So here we have our rotor, and this above this line, all of these circuits will be on the rotor side, and below this line, all of these circuits are on the stator side. So the synchronous machine itself starts from this place. So the main construction of the synchronous machine, it has the field winding, which needs a DC source, and it has three-phase winding on the stator side. So this part here up to here represent the synchronous machine. As you can see, this is the synchronous machine. So this is the main field winding, and this is the main armature winding. On the stator side, we still have another circuit, but it's not used for the power. This circuit, guys, is, as you can see, it consists of bridge rectifier. And this bridge rectifier is connected to a winding, or let's say as a part of a small machine. This small machine, we call it exciter. So this exciter, we will see the construction of this exciter right now. So the exciter consists of supplying three-phase through a rectifier to a DC winding. So if you can imagine with me now, guys, this is like a DC machine right now. So we have a DC winding, okay? This DC winding is connected to a rectifier here. So we supply this from the AC side. Since this is a rectifier, so this is going to be the DC side, and this will apply the DC to our winding right here. So we will have a DC current here. On the other side, we will have three-phase windings. So these three-phase windings are installed on the same rotor shaft of our machine. So what will happen if you have stator winding supplied by a DC and you have a rotor windings, three-phase rotor windings, and these windings are installed on the rotating object. So the rotating object is moving by means of the prime mover, like wind turbine, like steam turbine, whatever the mechanical turbine we have. So let's call it prime mover. So the prime mover will rotate these windings. So we have now a rotating windings and we have a source of flux. So, you know, guys, if you have a source of flux and you have a mechanical input power, so the third term that will be generated is electrical power. So what will happen is these windings will have a generated volt across the three phases, and this generated volt, don't forget that these windings are rotating object right now. So these windings will generate three phase. So we can use a bridge rectifier now. So this rectifier can convert this three-phase AC into DC and be connected to the same main field winding, since all of these three windings are installed on the rotor side. So this machine here, we call it exciter. So the exciter is nothing but a DC generator with rectifier. So this is a DC generator, but without commutator. We don't have commutator in this machine because we don't need to commutate the supply. We don't need to rectify the supply. We have already a rectifier here. So the generated AC supply here on the rotor side will be rectified by means of a rotating rectifier. So this rectifier is installed also on the rotor side. So this rectifier here is installed on the rotor side. So this will rotate all of the time and connecting the generated volt on the exciter, converting this AC volt into a DC volt to supply the main field winding of the synchronous machine. How the exciter here could generate this AC, let me show you that simply in another slide here. So we agree that we have now a DC winding on the stator side. So if this is the stator side and inside we have the rotor here. So on the stator side, we have the DC winding, or the AC supply is connected to the rectifier circuit. And the rectifier circuit will connect the supply to the stator winding like that. So these windings now will have DC. If this winding have DC, this means it will create pools. Assume that this pool here is N and this is S, and a flux will move from N to S and will return back through the core like that. So this is here the surface of the stator, and here we have the remaining part of the stator core. And this is also the same direction of flux in our stator. So this is the flux direction now, guys, moving from north to south. So On the other side here on the rotor, we will have our other windings. So the other windings are three-phase windings. Let's say phase A, phase B, and phase C. And this is the rotor, which is rotating already. So what will happen is phase A here will come and cut or will be cut by the the field lines and rotate and so on and come to the other side here to be cut of the field winding, but from source side, not from north side. So for every winding, guys, we will have AC supply. So this is A, and you will have B and C shifted by 120 degrees from the first phase. So the output of these windings now, guys, the output is three-phase AC. This three-phase AC will be converted now to DC by means of the rotating rectifier. So if you can imagine with me now, this is our shaft. We have here the exciter stator, which is supplied by our rectifier circuit from the three-phase AC. So we will have here DC flux, and the windings here will generate AC, which requires another device installed here on the rotor, which is rectifier. So this rectifier now will provide rotating DC source. And the rotor of the synchronous machine is already installed here. So we have the rotor windings of the synchronous machines, which requires DC supply. So we can connect now this DC supply from this rectifier. So could you imagine with me, guys, now? So all of this object now is rotating on the rotor side. And then the three-phase windings of the generator on the stator side will be receiving the flux coming from the rotor windings in order to generate the AC. So this is, guys, the concept of having brushless excitation. So we could supply the DC source to the field winding without having brushes in this case. But this is with the help of another machine, which is called the exciter. Again, guys, don't forget that excitation for machines is very small amount of energy or very small amount of power compared to the armature power. Okay, so we may have like several kilowatts of field circuit used in a machine of several hundreds of megawatts of power. So the field winding power can be neglected to the armature winding power. Okay, so this schematic is simple. I wish if you could understand now the drawings here. This is schematic again. So in this schematic again, guys, the lower part represents the stator or the stationary components. The upper part represents the rotor components, and the first vertical part here, this is the exciter. So this is the windings on the rotor side of the exciter. This is the windings on the stator side. Here we have a rotating rectifier, and this is the main machine, which is the synchronous machine. So we have here the field winding on the top, and here we have the armature winding on the stator side. So this is called, guys, brushless excitation for large synchronous generators. Now, we call this machine synchronous generator. Why we call it synchronous? So the word synchronous means we have two things are synchronized together or moving on the same time or the same frame. So everything between them is in harmony and moving in the same time. So for that, what are these two things that moving in harmony? Actually, this is the supply frequency and the rotor or the moving of our rotor or the rotating machine. So the speed and frequency are synchronized. This means if you have constant supply frequency, this machine speed is going to be constant. Someone can say, you said to us in DC machine, if we have a motor and you load this motor, it makes sense that the speed will reduce. Yeah, this is correct, but this is in DC motor. Here in synchronous motor, the speed will not decrease. But what happens? Actually, the torque will be affected. Because by the end, you have two terms of power. Mechanical power is torque times omega. Electrical power is volt times current. So if the speed is constant, the torque will be affected. So if you absorb more power, you load your machine by more power. This means instead of reducing the torque to have the same amount of power, you need to increase the torque to provide the same power required to your load. So this is the concept in synchronous machine. For that, guys, synchronous machine is preferred in constant speed control. If you have constant speed loads, we do prefer to use synchronous machines. For that, we do prefer to have synchronous generators because our grid has constant frequency. Our grid requires constant frequency, which is 60 hertz here in the United States. So why we call it synchronous again? Because the relation between synchronous speed and frequency is, as you can see, is linear relation. So N, synchronous speed, equals 120 times frequency divided number of poles. Okay. Regarding the excitation, guys, we already have a relation between generated volt and speed in case of DC machine, and we drive this relation together before. For the AC excitation, we discussed the DC excitation in the magnetic topics, but we didn't discuss the AC excitation. But the AC excitation has a long derivation. The long derivation leads to this relation here, which is, in case of AC excitation, the induced volt equals 4.44 times frequency of the supply times field of the supply, the generated field, times the N, which is number of turns of coil, number of turns per phase, times another factor called winding factor. So this winding factor, we assume that this factor is almost equals 1. So you can say by the end, the induced volt equals 4.44 times frequency times pi times number of turns. So we can say that frequency or EF, the generated volt, is proportional to frequency times flux. So the induced volt is proportional to frequency times flux. And this is the peak flux of our machine. So the magnetization curve or the open circuit characteristic of the synchronous machine can be like that, as you can see here. So if you would like to see the relation between the induced volt and field current, or the relation between flux and field current, actually this is the relation between flux and field current that we know from magnetic circuits. Okay, so you know if you have a certain electromagnets and you flow the current increase will lead to a flux increase until the core is saturated. So since the induced volt is a function of flux and frequency, so if we say that the frequency is constant, the relation between the induced volt and field current is going to be the same. So this is by the assumption of having constant speed. But if this speed changes, so if this is omega 1, so this will be curve number 1. If you have omega number 2, so you will have another curve number 2, and so on. So this is the relation between the induced volt and the field current at a constant speed. And again, guys, don't forget, there is a relation between the mechanical speed or synchronous speed and supply frequency. So you can say that this curve is at the rated synchronous frequency or our supply frequency, which is 60 hertz. Okay. So this is the relation of the induced volt. We mentioned, guys, that if you have 120 phase shift degree, you will have a rotating magnetic field. So what is the meaning of rotating magnetic field? And do we have other forms of magnetic field, either the rotating one? So there is a derivation for that, guys. So if we assume that we have a three-phase machine like that, these three-phase machines, as you can see, this is winding A. So this is the start of coil A, and the end of coil A here is called A prime. So this is phase A. Here, this is phase B, and this is phase C. So there is a phase shift of 120 degrees between every phase, and these phases or these windings can be connected as Y connection or as delta connection. So whatever the connection, guys, we have to have the 120 degrees. What the 120 degrees will make, so let's see this derivation together. If you supply the machine by the 3 AC supply, so we expect that the phases, the current phases, can be I maximum cosine omega t. If you assume that is cosine, if you assume sine, this is fine as well. It will lead to the same end of the derivation. So assume that we have IA equals I maximum cosine omega t. So if we have positive sequence, which means if phase A is at angle 0, so IB is going to be at angle 120 in negative. So this is IB equals I maximum cosine omega t minus 120, and IC would be I maximum cosine omega t plus 120. So this if the configuration of the machine has a mechanical phase shift that produce 120 electrical degree. And the magnetomotive force that will be generated for every phase is going to be, so the FA, you know, the magnetomotive force is N times I. So it can be N times IA cosine theta. For the phase B, it's going to be N times IB cosine theta minus 120, where theta is the angle, the mechanical angle. And if for phase C is going to be N times IC cosine theta plus 120. Now, if you substitute by IA, IB, and IC in these three relations, so replace IA by I maximum cosine omega t minus 120, and replace IB by I maximum as this longer relation. So we will have NI maximum cosine omega t cosine theta, NI maximum cosine omega t minus 120 times cosine theta minus 120, plus NI maximum cosine omega t plus 120 times cosine theta plus 120. If you would like to replace every cosine A cosine B by half cosine A minus B plus half cosine A plus B, so we have here cosine cosine. Okay, we have cosine A cosine B. So this is or we have cosine A minus B, we have cosine A plus B. So replace omega t by A and theta by B. So what will happen? You will end up with this relation. So the f of theta and t equals half ni maximum cosine omega t minus theta plus half ni maximum cosine omega t plus theta. So this is for the first term here because we have cosine cosine. Then for the second, apply the same relation here for the second part. So this would be half ni maximum cosine omega t minus theta plus half ni maximum cosine omega t plus theta minus 240. And then we will have half ni maximum cosine omega t minus theta plus half ni maximum cosine omega t plus 240. If you compare these terms, as you can see, these three terms are equal. And this is in the direction of minus theta. However, here, these are in the direction of plus theta. So if we consider the minus theta direction as the forward rotating component, so the plus theta is going to be a reverse or backward rotating component because it's in the opposite direction to minus theta. So in this case, guys, let's call this one forward rotating component. And as you can see, the three terms are equal. So we can say now we have 3 halves. And here, this backward component, one is at angle omega t plus theta. I can say plus 0. And another one, the same peak value, and the angle is omega t plus theta minus 240 and plus 240. Plus 240 is minus 120. So this means the summation of these three terms is going to be 0. If you have 3 vectors shifted by 120 degrees and having the same magnitude, so the summation is going to be 0. So this means the backward flux is eliminated because the phase shift between the 3-phase winding is 120. If the shift is not 120, this will not lead to 0. Okay. So by the end, the summation is going to be 3 divided 2 ni maximum cosine omega t minus theta. Cosine or sine, guys, is nothing but a rotating vector. For that, we can say, according to this derivation, the induced MMF of our machine is a rotating magnetic field. Why it's rotating again? Because it's a cosine function. And the phase shift of 120 degrees between the phases could cancel the backward flux in our machine and allow the machine to have a rotating magnetic field. So this is the conclusion of this derivation. If we don't have the 120 degrees between the phase shifts, if we have 2 phases, not 3 phases, if we have single phase, not 3 phase, for sure the magnetic field is not going to be rotating. Okay. And a rule for any rotating machine, guys, no machine will rotate without a rotating magnetic field. So if you have the magnetic field is not in rotating form, you will have a problem. You cannot rotate the machine. There is one of the machines called 2-phase machine, and we have one of the machine called single-phase machine. These machines need something to make start for the motor. It cannot start automatically. But 3-phase machine can start automatically because it has a rotating magnetic field. Okay. So let's stop at this point right here and continue our next class starting from the equivalent circuit model of the synchronous machine. Thank you so much and see you in the next class.